In this series, we will look at k-nearest neighbors, shortly KNN. In this video, we will look at the basics of the KNN classification algorithm. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. Let's look at the full table of contents. This series mainly covers classification and regression with KNN. In the classification section, we'll briefly look at the history of KNN, an overview of KNN and the algorithm, and we'll implement a KNN classification model from scratch, and implement it using a library called K-Neighbors Classifier in scikit-learn. Then we'll compare the two results. We'll take a look at the weighted KNN, a variant of KNN, and see how it handles categorical features. We will learn how to measure the distance or similarity between categorical features. We will also discuss how to use IOF to compute distances between categorical features. And then we'll take a look at the basic algorithm of KNN regression. KNN regression can use either the simple average method or the weighted average method. Let's take a brief look at the history of KNN. KNN is a very old algorithm that was first proposed in 1951. According to Wikipedia, Evelyn Fix and Joseph Hodges first proposed KNN in this paper. And later, Thomas Cover further extended this algorithm. Now let's look at the KNN classification algorithm. First, let's look at the training and test data below. This data has two features, x1 and x2, and a target class y. x1 and x2 have real values, and y has three classes, 0, 1, and 2. If we visualize these data points, it would look like this. Each data point can be represented as a single point on the x1 and x2 axes. And the y values 0, 1, and 2 can be distinguished by different colors like this. If y is 0, this area is colored red. And if y is 1, colored blue. And if y is 2, it's colored green, like this. The test data also consists of two features, but without the target class y. Our goal is to use this training data to estimate the class y of this test data. Let's plot these two test data points A and B in the feature space like this. We want to use the KNN algorithm to estimate the classes of the test data points A and B. Now let's take a look at the KNN algorithm. In the first step, we compute the distances between each test data point and all the training data points. In the second step, we find k neighboring data points close to each test data point. For example, setting k to 10 will find the 10 closest neighbors to each test data point. Let's draw a circle like this around each test data point so that it contains 10 training data points. This circle contains 10 data points like this. These are the closest neighbors to this test data point. In the third step, we use the training data to find classes of these 10 neighbors. For the test data point A, the classes of all the training data points within this circle are all 1. For the test data point B, this circle contains 8 data points with class 2 and 2 data points with class 0. In the fourth step, we find the majority class of the nearest neighbors and then classify the test data point into that class. That is, it is decided by majority vote. Since all of the neighboring classes of the test data point A are 1, we can confidently estimate that the class Y of this test data point is 1. This data point has similar properties to the data points belonging to class 1. For the test data point B, there are 8 data points with class 2 and 2 data points with class 0 inside this circle. So we can estimate that the class Y of this test data point is 2 with 80% probability. This data point has similar properties to the data points belonging to class 2. In this example, since the data is two-dimensional, it is easy to estimate the classes even with the naked eye. But this is not the case for high-dimensional data. Therefore, we need a generalized algorithm like KNN. Next, let's take a look at some issues to consider in KNN. The first problem is how to choose the value of K. You need to decide how large a circle to draw around each test data point. The second question is, what kind of distance should we use to measure the distance between a test data point and a training data point? There are several methods to calculate the distance between 2 points, such as Euclidean and Manhattan. You need to decide which type of distance is best for your data. The third issue is that high-dimensional data can cause the curse of dimensionality problem. The fourth problem is that it takes a long time to compute the distances between each test data point and all training data points. The fifth question is how much weight should be given to each distance. In this example, we had equal weights to all distances. However, there may be cases where different weights need to be given to each distance. We will look at these in more detail one by one later. Next, let's look at how to compute a distance matrix using array broadcasting. Given 5 training data points and 3 test data points, we want to compute pairwise distances for all combinations and produce a distance matrix like this. This element represents the distance between the first test data point and the first training data point. And this element represents the distance between the first test data point and the second training data point. You could use 2 for loops to calculate the distances one by one, but you can do it more efficiently using array broadcasting. Now let's look at how broadcasting works with arrays of different dimensions. We have training data X and test data T like this. X is a matrix with 5 rows and 2 columns. And T is a matrix with 1 row and 2 columns, containing only a single data point. Let's compute X minus T. Computing X minus T might seem impossible because X and T have different shapes. But broadcasting T in this way makes this computation possible. Duplicate this vector downwards, and then compute the values of X minus T. The difference between this vector and this vector is computed. And the difference between this vector and this vector is computed. The result is a matrix with 5 rows and 2 columns. Let's make a simple rule here. If the numbers of columns are the same, and if the number of rows on one side is 1, broadcasting occurs along the row axis as many as the number of rows on the other array. The number of rows on one side must be 1. If it is 2 or 3, no broadcasting will occur. And x minus t cannot be calculated. Now let's consider this case. The test data contains multiple data points. In this case, broadcasting becomes a little more complicated. We want to compute all the distances between training data points and test data points. To create a distance matrix like this, the first subscript of D indicates the row number of the test data, and the second subscript indicates the row number of the training data. For example, this element represents the distance between the third test data point and the first training data point. This is the distance, D31. We need to compute a total of 15 distances. This distance matrix is a 3 by 5 matrix. Calculating x minus t requires broadcasting. To do this, we need to convert these matrices into a 3-dimensional array. Insert a new axis to matrix X along the first dimension, and insert a new axis to matrix T along the second dimension. If you draw the converted 3D array, it will look like this. The data points 1, 2, and 0, 1, etc. are arranged along the axes D1 and D2, like this. And a new axis D0 has been added to X. For matrix T, the axis D1 has been added. The test data points 1, 1, and 0, 0, etc. are arranged along the axes D0 and D2, like this. Then the shape of the 3D array X' becomes like this, and the shape of the 3D array T' becomes like this. Now let's calculate X' minus T'. Let's apply the rule we created on the left. The last dimensions are equal, and the first dimension of X' is 1. So it increases to 3 via broadcasting. The 3 is the size of the first dimension of T'. That is, broadcasting occurs along the axis D0. And since this dimension is 1, this also increases to 5 via broadcasting. The 5 is the size of the second dimension of X'. Broadcasting occurs along the axis D1. Then the shapes of the two arrays will be identical. Therefore, X' minus T' can be calculated. The result is a 3-dimensional array, 3, 5, 2. Now let's calculate the Euclidean distance between the first training data point, 1, 2, and the first test data point, 1, 1. The distance can be calculated like this. This part in the parentheses is X minus T. Taking the square root of the sum of squares of X minus T gives us the distance. Since we are summing along the axis D2, the last dimension is gone. So the final result will be a 3 by 5 matrix. This is the distance matrix at the top right we wanted to find. Next, let's write a Python code to find the distance matrix using this method. Add an axis at position D0 of the training data X, and add an axis at position D1 of the test data T. Taking the square root of the sum of squares of X minus T gives us the distance matrix. This is the distance matrix with 3 rows and 5 columns on the top right corner. Broadcasting makes coding easier than using multiple for loops. Next, let's write a code that generates a distance matrix using broadcasting and performs classification using the KNN algorithm. Let's create a dataset we'll be using. Let's use the makeBlobs function to generate data like this. This dataset has 2 features, x1 and x2, and one target class y labeled 0, 1, and 2. We will generate a total of 300 of these data points. If we plot these data points in 2-dimensional space, it looks like this, right here on the right. The data points where y is 0 are distributed in this area marked in red. The data points where y is 1 are distributed in this area marked in blue. And the data points where y is 2 are distributed in this area marked in green. The center of each distribution was set as follows. Since the number of centers is 3, the number of classes generated is also 3. And the standard deviation of each distribution is set to 0.15. And the range of the data is set to -1 to +1. Here's the code to visualize the data points like this. We then split this dataset into training data and test data. The training data is xtrain and ytrain, and the test data is xtest and ytest. And the k-value of KNN is set to 10. Let's assume we don't know the class ytest of the test data and estimate it using the KNN algorithm. First, let's use array broadcasting, which we looked at on the previous page, to create a distance matrix between all test data points and all training data points. Add an axis at position D0 of xtrain, and add an axis at position D1 of xtest. And then we use the 2 expanded arrays to generate a distance matrix. The distance matrix was computed as follows. The number of training data points is 225, and the number of test data points is 75. Then the distance matrix will have 75 rows and 225 columns. The first row shows the distances between the first test data point and all training data points. And the second row shows the distances between the second test data point and all training data points. Next, for each test data point, we find the k nearest neighbors. We find the shortest k data points along the axis D1. This is the array I near, and it looks like this. For each of the 75 test data points, we found the 10 nearest neighbors. I near is a 75 by 10 matrix. The first row contains the indices of the 10 training data points closest to the first test data point. The first element shows that the distance between the first test data point and the 86th training data point is the shortest. And we find the classes Y of these neighbors. That's the array Y near, and it looks like this. Y near is also a 75 by 10 matrix. The first row shows the classes for the 10 closest neighbors to the first test data point. The first number 1 indicates that the class of the 86th training data point is 1. Finally, we estimate the class of each test data point via majority voting. The first test data point is estimated to be class 1 since all of its neighbors have class 1. The second row has 4 2s, 4 0s, and 2 1s. Since the numbers of class 2 and class 0 are the same, we assume that the class of the second test data point is either 2 or 0. The third test data point is also estimated to be class 1 because all of its neighbors have class 1. In this way, we estimate the class Y for every test data point. This is the vector Y_pred. Now that we have estimated the classes Y for all test data points, we can measure the accuracy of this model. Y_test contains the actual values and Y_pred contains the estimated values. Accuracy is a measure of the ratio of the number of matches between elements in the two vectors Y_test and Y_pred. The accuracy is 94.67%. Let's run this code. This time the accuracy is 93.3%. So far, we have looked at the basic algorithm of KNN and written a code to perform classification using KNN. In the next video, we'll look at different types of distances, decision boundary, and the optimal value of K.